We're going to veer away from talking about light just for a little bit and talk about something called the Doppler effect instead. And if you want the wordy definition, it's the apparent change in the frequency of a wave due to the relative motion of the observer and the source. So the example that we're all familiar with is a car going down a road, toots their horn, and you on the side of the road here, you're smiling because you're thinking about physics. As the car goes past, you'll hear this meow, where the pitch appears to be high pitch before it passes you and low pitch after it passes you. And the reason for this is the Doppler effect. Let's now pretend we have a stationary car and it honks its horn. Well, the sound waves that it emits are going to be the same frequency in all directions. But now, let's say that the car starts moving forwards, and we have an observer standing still on the right and an observer standing still on the left, also happy because they're doing physics. The compressions and rarefactions are going to be closer together to the observer on the right, and they're going to appear further apart to the observer on the left as the car moves further away from them. Now, this might seem like a bit of an abstract concept, but basically, if we assume that the car's horn emits waves periodically, it's going to be closer to you every time it emits a wave, if you're on the right. And if you're on the left, it's going to be further away from you every time it emits a wave. And if the waves are getting closer together, that's an increase in frequency. And if they're getting further apart, that's a decrease in frequency. So you can see how this effect can unravel. Now, if we want to do the maths behind this effect, we need to define a few terms. So F0 is the initial frequency, F is the observed frequency, V is the speed of sound, VO is the speed of observer, and Vs is the speed of the source. Now that we know all this, we can write our equations. And we need two equations. One of them refers to two objects coming closer together, like on the right, and one of them refers to two objects moving away from each other, like on the left. If the objects are moving further apart, we write F equals V minus V0 times F0 over V plus Vs. And if the objects are moving towards each other, we write F equals V plus V0 times F0 over V minus Vs. So what you'll notice is the signs here and here, and the signs here and here are always the opposite of each other. So all I do is remember that if we are moving towards each other, that's a plus sign. If we are moving away from each other, that's a minus sign. And the sign on the bottom is just the opposite. And the other thing we can do is if the observer is stationary, then we can just put in a 0 here or a 0 here and write that F is V F0 over V plus Vs, or V F0 over V minus Vs. And the same effect happens in stars and planets when we're looking through a telescope. Let's just call them celestial objects. And if the celestial object is moving across the screen left to right, and this is you looking through your telescope, then the wavelengths of light that this object emits are going to be elongated. In other words, the frequency is going to decrease. And if the frequency decreases, then the wavelength increases. And we call this a red shift because the wavelength gets closer towards red on the spectrum. Remember, blue is the shortest wavelength, highest frequency. Red is the highest wavelength, lowest frequency. And you can probably see where this is going. If this is you and the celestial object is coming towards you, as you look through your telescope, you're going to notice a blue shift where the light that's coming in tends towards blue. And this is because the frequency is increasing, therefore the wavelength must be decreasing. So this has been a discussion about the Doppler effect and the formulas that we can use to analyze it. And if you ever forget what the Doppler effect is, just remember, meow. And remember to email us any STEM questions you might have using the link in the description.